Hi everybody. So if you read what I posted online, I was going to try something different today and go through the answers that were posted today already with you, because I think there's some margin notes and some different little highlights that you can make on your work. And you have to remember, you're not just learning how to do this for passing this class and doing well on the tests and quizzes, but you have to walk into university in September and possibly a first year introductory physics class, and you need to know how to do this stuff. So let's get some other details on here. I want you to print these pages, or at least look at them online first and go through all your work in comparison to these pages. So if you haven't done that yet, stop this video, pause it, whatever, and do that first before you continue on. Now let's put some additional notes on your solutions and on my solutions here. So first of all, for question one, you want to start question one off just like this. You want to have the diagram and the charges only. No numbers, nothing else, no distances. You want to start off these systems of electric force questions by looking at just the charges. These are 3 positive charges in this question. And before you even begin the question with calculations and numbers, identify which charge they want you to look at. In today's question, I want you to look at the lower left-hand corner and focus just on that charge, kind of ignore the rest of the diagram, and ask yourself, what are the forces that this charge is going to feel because of the other charges? So first of all, between these two on the bottom, they're going to repel each other because like repels like. So this charge in the bottom corner is going to feel a force away from this charge over here on the right, and I'm going to draw that on there. And similarly, between these two charges, it's a further distance, but there's still going to be a force or repulsion between just these two charges because like repels like. So although this charge up here will feel a force away from this charge down here, we're not concerned with that. It's not asking us about that corner. But in this corner down here, there will be a repulsive force between those two charges. And you want to do this right away before you start the question. You want to set up a diagram so that you know what it's going to look like in the end. So you need to figure out 2 forces here. You want to determine what the force is between A and C, and you want to determine what the force is between A and B. A and C is actually the same as it was in the previous day's work because you had already done a calculation between those two charges when you were looking at the lower right hand corner. So you actually still have a value for that. It was 360. You'll need to calculate the force between these two charges, and you can't just repeat work from last day because you never did have this distance, side C of this right angle triangle, and now you need that distance. So let me go to the work pages here and let's see where we are. So on the solutions that I posted online, I did repeat the calculation for the interaction between the first two charges and got 360. The next calculation, I started off with the hypotenuse distance between the charges on the side that we never had worked out the previous day. And using that new distance, another Coulomb's law calculation simply for a force, but with the new distance on the bottom, and of course remember to square it. It's in scientific notation already, and you're going to find that when things are in scientific notation, you're going to forget to square them. That force comes out to 180.44. So now that basically means this. Going back to the diagram that I sketched on a piece of paper before opening this sheet, we've got 2 forces, a 360 Newton force horizontally to the left and this 180.44. And luckily in this question, because of the symmetry, you didn't have to work out this angle. You could surmise it was 45 degrees just based on side A and B being the same. But normally you'd have to do a tan calculation and determine what the angle is in here. But this time 45 degrees. So you need to take the component that's on an angle, and the vector that's on an angle, and break it into its components. I did that here. So this isn't the whole diagram, this is just the 180.44 Newton vector broken up. And then finally in the end, once you've broken the angled vector up, you'll have components that are all up, down, left, and right, and you can put them together into one final right angle triangle, and hopefully you know where to go from there. Pythagorean theorem to solve for the net force, and a trigonometry calculation to get the angle inside. I only wrote down one answer here, 504 newtons left, 14.7 degrees down, but of course the complementary of this would also be valid. You could say down, complementary of that, degrees up. But for university next year, when you have two versions of an answer and two different angles, the standard is to go with the smallest angle. So I could have had an answer instead of 14.7, I could have had an answer that was down 75.3 degrees left, but this is the more proper answer because the magnitude of the angle is smaller. And that's a note that you might want to put on your work too. If you had 75.3 degrees, it's not wrong, but chances are next year they wouldn't accept it and they would want you to put the smallest version. Question 2. This is a really easy question, and it's a very standard question. You get these all the time. They will give you two charges, and they will ask you where to place a third one for some condition to be met. The easiest question is actually this one. Where in between would you place that third charge so that it would have no net force on it whatsoever? Now, I did this. I said right away that the understanding in this question is the force of repulsion. And actually, come to think of it, I wrote these backwards. You can fix that if you like. These are all positive charges, and like repels like. Now, it's not going to change the answer. The answer is going to be exactly the same. But technically, this isn't the force between 1 and 3. This would be the force between 3 and 2 because it's a repulsive force between those two charges. And similarly, these two charges, both being positive, would have a repulsive force between them. And this would be force 1 and 3, or the force between 1 and 3. So I had those backwards. Not a big confusing thing, but something that you probably should fix. Now, if you don't like this, if you say to yourself, I'm not sure if I could have just made that equation right away, here's something that you can add in. Don't forget, this question really was this. The net force on this charge would have been the difference between these forces because they're in opposite directions. And so let me just write it like this. You could have solved for the net force by saying force between 1 and 3 is to the right, so I'll make that positive, and you would subtract off, because it's in an equal and opposite direction, the force between 3 and 2. I mean, technically, that really is the formula that you should be starting with, but we know from the conditions on this question that the net force is 0, that it's going to be completely balanced. So with a 0 on the left-hand side, you could then take this negative force, bring it to the other side, and you would have this. So technically, I guess, starting with force equals force is really sort of the second line of work. But at that point, the question is very easy because with no plus and negative signs in there, there's a lot of things that cancel. So when you write Coulomb's law on both sides of this equation, you've got a K and a K. They cancel out. And one of the charges cancels out as well. On one side of the equation, it's Q1 and Q3 multiplied together. On the other side, it's Q3 and Q2 multiplied together. Well, the Q3 will cancel, left side, right side. So that really makes things a little bit easier. Hopefully you weren't confused with the conditions on distance in this question. You don't know what this distance is between these two charges, and you need to find that. So I identified that distance as x, and the only way that you can solve for that x is you need to know what the distance is between these two charges. We don't have that either, but it did say originally that the two charges before placing the third one in between were 90 meters apart. So hopefully you understand why one of these distances is x, and the other one, although you don't know the value of it either, it would be 90 minus x. And then whatever x is, that would make it all work. So what that's going to do is it's still the same unknown. It's still an unknown x, but it's going to occur more than one time in the formula, and you'll have to collect like terms. So that's what I did down here. I substituted in actually two things at once. I substituted in the charges, and I know it's a little bit confusing because the general variable for charge is Q. And so on this line, I've got Q1, meaning the very first charge, and Q2 is the second charge on the right. But then they go and tell you the values for those charges. And they tell you that the value for one of the charges is plus Q, and the value for the other charge is plus 3Q. So don't be confused with that substitution there. Q1 and Q2 are general variables. This Q and this 3Q are more specific substitutions. Now notice how I didn't put the plus signs in here, and if you think back to work from previous days, I said that before. Don't use signs when you do the equations. Only use your plus and negative signs to set up the diagram in the beginning and think about how the arrows are going to work. So in this question, what I mean is drawing these arrows here, that the directions of those arrows had to do with these plus signs and the repulsion or attraction, if there was some, between charges. So the setup of these vectors is what leads to this formula here. I could not have wrote that formula if I didn't consider the directions on those vectors, and the only way to consider those directions are to look at the charges. But once you've got that formula written and you start working with it, you've already dealt with the charges. It doesn't really make a difference if they're positives, but sometimes they're mixed, they're negatives and pluses, and if you go and put the signs in here by accident, you'll make math errors, because you might have two negatives making a positive, and you'll end up getting different magnitude answers on the end. Anyway, so when you sub in the distances here, everything's fine except for this. This set of brackets being squared, you may have forgotten how to do this. It's not 90 squared plus x squared. Be careful that you didn't do that. You've got to FOIL those brackets out, just like you did in previous grades. That's 90 minus x times 90 minus x. And remember, you have to do this. 90 times 90, 90 times negative x times 90, negative x times negative x. There's a full FOIL that you have to do there. So I'll probably let you go through the rest of this question on your own, because it's all just math details. I FOILed the brackets, I cross-multiplied, I collected like terms, I pushed everything to the left, I identified quadratic A, B, and C, and subbed it into a formula and solved. Now, I want to point this out, though. Up until now, you've always thought that you're going to get a positive and a negative answer to quadratic formula, and it'll be obvious which one is right and which one's wrong. Not in this case. They're both positive. So you have to figure out which of these two answers is right. And luckily, the answer makes sense because the distance between the charges is only 90 meters. So 212.94, that can't possibly be right. It's got to be 57. But I want you to put a couple of notes on here and not leave this question so blank. This makes sense. It's not just a shot in the dark answer. I actually drew the diagram slightly wrong in the beginning, and I want you to consider this. If you have a charge of Q and a charge of 3Q, and you want to put a charge in between them and have it balance out, this is a much stronger charge. A much stronger charge means you can get further away from that charge and still have enough force to equate the smaller force that you might get from this charge. Remember, the third charge is Q. So it does make sense that because this side is bigger and there's going to be more of a repulsion coming from the right than there is from the left, the distance in the end should be a little bit further to the left of the diagram than to the right of the diagram. And so when you get an answer of 57 meters, that actually sounds right. If it was less than 45 meters, it would be wrong. There would be no possible mathematical way that would happen given the conditions of this question. What about the 212? Well, and this is worth making a margin note about because it is kind of interesting. The original formula, the way it was written in this question, was just that force was going to equal force. That was it. Those were the two conditions. That the force between charge 1 and 3 and the force between charge 3 and 2 were going to be equal. It had nothing to do with directions at this point. It was just the force was going to equal the force. Well, if you had an answer way out here, diagram, I'm going to just draw across my written words here. If you had an answer out here somewhere, and that was a plus sign, that would also work, because the force between these two would be repelling, and the force between these two would be repelling as well. And because this charge is much greater, there would be a position out here where you could actually have these two forces equal, but they wouldn't cancel each other out. They're not in opposite directions. So that's what that other answer is. There is a spot 212.94 meters away from that charge where those two forces are indeed equal in value, but they're both pointing in the same direction because of repulsion. So the question works magnitude-wise, but it doesn't work in a realistic sense, because then this particle would be pushed to the left with two forces and it would move to the left. The last question, I wrote quite a few notes about it, so I'm not going to say too much about this one. And actually my battery light is blinking on my camera of all things. So if this video cuts off, read the hints for this question. I'm going to talk as long as this battery keeps blinking, and I'll see if I can fit this in. This is a really common question. And this diagram is so important up top here, because this is what you have happening. You have two electrons, like repels like. So if this one's sitting on the ground, it's actually going to be repelling the one above it. That's what that upward force is, the repulsion between those electrons. But the idea in this question is, it's an electron, it's got a real mass, and anything that has a mass has a force of gravity on it. So the Earth would actually be pulling down on that tiny little mass, and it will remain hovering in the air if these two forces cancel out. So once again, you can add in a line if you want, saying that the net force in this question is going to be whatever the electrical repulsion force is minus gravitation, because it's in an opposite direction. And this is balanced. The net force is 0. So again, if you take this negative Fg and bring it to the other side, you get this. So you can kind of start in one of two spots. You can start right here if this makes total sense to you, or you might want to write this line above it, slash out the net force and make it 0, and rearrange and come up with this idea that the two forces are equal. And then it's actually a very easy question from that point forward. You've got two charges and they're both the same value. They're both electrons. And again, you don't need to use a negative sign for an electron charge, because the negative sign, that implied repulsion between the particles, and that's already dealt with in the diagram. So combine those two Q's together, it'll be charge on an electron squared, because you're multiplying two Q's together, and just rearrange. Just rearrange for the distance, sub in your values, and don't forget to either root the entire right-hand side when you isolate, or make sure that you realize it's d squared on the left-hand side, and you have to root the answer in the end. I put the unsquare rooted answer on here just in case some of you got 25.8. You would realize from my solution that you still have to root it, and you end up with about 5 meters in the air above it, which is kind of cool, because when you think about it, that's the only answer. And you will get this question again. It won't have any variation to it, because they can't make it an electron and a proton, for example, because they would attract each other. And there would be no way to hover one over the other. I guess the only other version of this question you could see next year is if they were both protons. But you do the question exactly the same way, just the mass would change. Remember, protons have the exact same charge as electrons. They're just positive signs instead, but they do have a different mass. So I think that's it for this video today. The only other thing maybe you might want to throw on here, just for interest's sake, is if you've got all your units on here properly. I noticed that 9.8, you should use newtons per kilogram as the units a lot more often now than you did in grade 11, because you'll see a lot of cancellations. Remember, university is going to make you show how these units cancel out. And if you look, there's kilograms times kilograms, they cancel. There's a Newton here and a Newton in the K constant, they cancel. there's a charge in coulombs, C, that's going to be squared. That'll make it C squared. That cancels with C squared, leaving you with just meters squared as the units, and this is still D squared. So you still have to root the right-hand side. So 25.8 is meters squared, and then you root that answer in the end for 5 meters. Final answer.